In this video, I'm going to do an example of another graph called a hyperboloid of one sheet. Okay, so let's take a look at the example. We're being asked to sketch this equation, and it is not any of the ones we've considered so far, not a sphere or a cylinder, not a paraboloid or a plane. When we don't know what to expect, then we need to go through the whole process of graphing all the traces. So let's take a look. As I mentioned on the last example, the way your book will do this is jump right to the general case of x equals a constant. You're welcome to do that if you're ready to jump right in and do that. I'm going to start slowly, and I'm going to look at x equal 0. If I put x equals 0 into my equation, I get y squared minus c squared, y squared over 4 minus c squared over 4 equals 1. Take a minute, pause, see if you know what that is and how to graph it. Okay, that is a hyperboloid. When you have two variables and you have squares, but their opposite sign, you have a minus, that's a hyperboloid. And quickly, the way we graph those, underneath the y is a 4, square root of 4 is 2. Underneath the z is 4, square root of 4 is 2. If I'm looking in the y-z plane, we draw in as if we're going to draw that ellipse 2 units in each direction, but instead we draw this rectangle very, very lightly. And then we draw the diagonals of that rectangle very, very lightly. We have a hyperbola, and the y is first, so I always remember that as it opens in the y direction, opens about the y-axis. So we have a hyperbola that looks like this. So if that seems rusty to you, go back and review conic sections. Okay, what does that mean about what's going on over here? And x equals 0, so when we're in the yz plane, set up my scale here, we have a hyperbola that has the vertices there at 2 and -2. Now, I'm not going to draw that whole box and the asymptotes and all that. In fact, as we go on, you don't need to get in that much detail. Basically, what you want to know is that you have a hyperbola. You want to know where those two vertices are, and you want to know about how wide or narrow it is. So that would be fine here. You don't have to show all that. I was just reviewing it for you. Okay. What about if I put in, say, just to make it easy, let's go ahead and look at y equals 0. If I put in y equals 0 into my equation, in the xz plane, again, it's a hyperbola. This, because it's a difference and it's squared, it opens around the x direction, the x-axis. Roughly, I'm going 2 units in the z direction and only 1 unit in the x direction. So again, you don't have to draw this in, but it is a little bit wider opening. Mostly I care that you get that it opens in the x direction. So where is that in my surface? Again, the xz plane is this side wall coming out at you here. So you're going to be drawing, it's always the hard one to draw in the xz plane because that's where we lose our depth perception a little bit here. We're going through x equals 1 and we're coming forward toward you. backward and then forward toward you. And then there's one back here too at x equals 1 going backwards. Okay, that starts to get really confusing looking. So sometimes I hold off on drawing in the xz plane till I see what else is going on. Okay, excuse me. If I let x or y equal a number, because of this minus z squared, I'm going to get a hyperbola every time. Hyperbolas are a little harder to deal with. But notice if I let z be a value, I'm going to get x squared plus y squared over 4. I'm going to get some sort of ellipse. So maybe I want to spend some time with that instead. Let's put in z equals 0. If I put in z equals 0 into my equation, I get x squared plus y squared over 4 equals 1. So that would be in the xy plane, an ellipse, 2 units in the y direction, 1 unit in the x direction. So bringing that over to my three-dimensional graph on the floor, on the xy plane, in that gray plane there, we have an ellipse that's 2 units in each of the y directions and 1 unit in each of the x directions. Something like that. All right, let's jump into maybe a little more involved cross-section, or a little more general cross-section, I should say. Let's look at z equals a constant. Because what I mentioned is that for any value of z, it looks like we're going to get ellipses. Let's see if that's the case. So z equals a constant. I get x squared plus y squared over 4 equals 1 plus k squared over 4. This is a positive number. So I get the sum of squares as a positive number. That's going to be an ellipse. If I put it in standard form, I'm not going to simplify it here. I'm just going to put 1 plus k squared over 4 and 4 times 1 plus k squared over 4 equals 1. So we see here that for any value of k, this is positive, positive equals 1. For any value of k, we have ellipses. This denominator is bigger than this one. So the axis in the y direction is longer than the axis in the x direction. And as k gets bigger, my ellipses are getting bigger. So that means in any cross section where z equals k, we're going to get some sort of ellipse like that. I didn't make it to any sort of correct scale there. That means when z equals 1, I get some sort of ellipse. Z equals 2, I get some sort of bigger ellipse. Z equals 3, I get some sort of bigger ellipse. Same going down. When z equals -1, I get a bigger ellipse than that green one, and so on. So you can start to see it take on shape a little bit. Those red cross sections still are a little challenging, but if I take them out for a second, kind of haphazardly, you can get a feel for the shape of that surface. It's hollow in the middle, and it's got these bending sides like this. Now, if I gave you this picture and I said, what is the cross section when y equals 0, then you could kind of say, oh, okay, I'm going to slice it this way, slice it down like that. Then you might see a little bit more clearly, oh, I'm going to get a cross section that looks kind of like this, hyperbola front and back. Right? Now, one other thing that I didn't look at here that your book does is, remember how back here I told you you could jump right into x equals a constant instead of just looking at a specific value of x? Let's suppose I did that. If I let x equal a constant in my equation here, I get k squared equals y squared over 4 minus z squared over 4, whoops, equals 1. This is a plus. So y squared over 4 minus z squared over 4 equals 1 minus k squared. So if we look at that, we might think, okay, that's a bunch of hyperbolas that open in the y direction. When k gets bigger, this is getting bigger, and you might start picturing that you're going to get more and more hyperbolas. But in fact, that's not what happens. This, when k is less than 1, between -1 and 1, this is positive. And so yes, you would get a hyperbola that opens in the y direction. But as k gets bigger, this is negative. When this is negative, this is not a hyperbola that opens in the y direction. Let me show you what I mean. Let's specifically put in x equals k equals 2. So we're looking at the cross section 2 units out here. If we do that, we would get y squared over 4 minus z squared over 4 equals 1 minus 2 squared. So -3. We divide by -3, we get y squared over -12 plus z squared over plus z squared over 12. So negative z squared over 4 divided by -3 equals 1. And so if we put that in our standard form, notice it's the y that's negative. So it's z squared minus y squared. So what does that mean? It means that where x equals 2, we actually have a hyperbola that is opening in the z direction at square root of 12 there. So that would mean that when x is 0, we had that hyperbola that looked like that. But now if we move forward and we take a slice further forward, we actually are going to get hyperbolas opening the other way. That starts getting kind of hard to picture. But that's exactly what we saw in this animation from earlier. Notice I have the hyperbola opening front and back. I'm sorry, top and bottom. As this plane slides backwards, then we get the ones that open sideways. So hyperbola is opening up and down, and now sideways. That's a hyperboloid of one sheet. So the general form for a hyperboloid of one sheet looks like this. Notice we had a minus with the z squared, and that opened around the z-axis. The z-axis was that axis of symmetry. So 2 pluses and a minus. Notice here, this time I have 2 pluses and a minus with all my square terms, only the minus is with the y. That's also going to be a hyperboloid of one sheet, but it's going to open around the y-axis. Here we have 2 pluses and a minus, but the minus is with the x, so that's just going to be a different orientation. That's going to be a hyperboloid of one sheet that opens around the x-axis. So what you want to remember is a hyperboloid of one sheet is when you have all 3 of the squares, 2 of them are positive and 1 of them is negative. The one that's negative, the one that's different, that's the axis that the graph opens around.